Hi everyone, so what we're going to try and do now is we're going to try and use a rate equation. There's a rate equation where the rate is equal to the rate constant K multiplied by the concentrations of whatever's in the rate equation. And we're going to use that to try to calculate either a rate, the rate constant, or the concentrations of the substances in the rate equation. And the examples I'm going to concentrate on are from the Kinetics booklet, Task 5, Question 1. Now all of these types of examples rely on you being able to interpret data and manipulate that data. So let's have a look. You'll always be given some data, and in this example you're given the concentration of G, the concentration of H, and the rate. Remember that the square brackets indicate the concentration in moles per decimetre cubed. So the data that we're given with to start with is concentration of G 0.2, concentration of H 0.1, and the rate 0.4. Then the first example that we're asked to find something out about is we're given a concentration of H, which is 0.05, and the concentration, we're trying to find the concentration of G, and we're told that the rate is 0.2. So immediately what we try to do is we try to use the factor that one of the concentrations has decreased or increased by and relate that to how the rate has changed, knowing the order of reaction with respect to those different substances in the rate equation. So let's just look at those orders of reaction. We know from this rate equation that G is first order, and we also know that H is first order. And again, we'll just remind ourselves what that means. First order means that if we double the concentration, we'll double the rate. If we triple the concentration, we'll triple the rate. If we multiply by concentration by 10, we'll multiply the rate by 10, and so on. It's important to know as well that if we divide the concentration by 5, the rate will also divide by 5. So it's a directly proportional relationship. So what we can see is that the concentration of H has gone from 0.1 to 0.5. So we can see that's halved, and we can also see that the rate has halved, and that's what we'd expect. We'd expect that the rate would halve if the concentration of H halved. But what we need to work out is the concentration of G. Now, all of the change of the rate has been accounted for by the change in concentration of H. So if we were to change G, because it's first order, if we were to double it or halve it, that would affect the rate. But the rate has already been accounted for by the change in the concentration of H. So that means that the concentration of G must be unchanged. It must be staying the same. And for all of the subsequent questions that we're going to do on this, we're going to compare it to probably the example data that we were given there. You don't have to compare it to this one, but that's probably the one that I will. Let's look at the next one. We're told that the concentration of H is 0.2 and that the rate is 0.4. And again, we want to concentrate on finding the concentration of G. So we can see that the concentration of H has doubled from 0.1 to 0.2, so that should cause a doubling in the rate because H is first order. So we would expect the rate to have gone from 0.4 to 0.8. Let's just write 0.88800 there. That's what we would expect it to be. However, it's not. It's 0.400. So that means the concentration of G must have changed to halve that rate from 0.8 to 0.4. it's half what we would expect. Because G is first order and the rate is half what we'd expect, the concentration of G must have halved from 0.2 to 0.1. So these are quite simple examples, and the data is quite friendly here. As you try more and more difficult examples, some of the data is in standard form, some of the numbers are not so easy to work with, some of the factors that the concentrations have been increased or decreased by are not whole numbers, and that makes things more problematic. But let's stick with something straightforward for now. Let's try the next one here. So we're told that the concentration of G is 0.05, the concentration of H is 1.000, and we want to find the rate. So again, I'm still going to compare with the original set of data there. So the first thing that I'm going to work with is the fact that H has been multiplied by 10. That is a tenfold increase of H. H is first order, there's a tenfold increase here, so you would expect the rate to increase by tenfold as well. So from 0.4 to 4.00. That's what we'd expect it to be. But we also have to take into account how the concentration of G will affect that rate. So we expect it to be 4 based on how H has changed. But G has gone from 0.2 to 0.05. So that is a quarter of that. So the concentration of G has gone from 0.2 to 0.05. Now, if you want to find out what that factor is, we'll just say 0.05 divided by 0.2, and that is 0.25, which is a quarter. So G has been divided by 4. That means this rate must also be divided by 4. Let's just go over this again, because it starts getting complicated. H multiplied by 10, so the rate multiplied by 10. G divided by 4, so we need to divide this rate by 4. So 4 divided by 4 is 1. So the rate that we would expect is 1. Okay. Next one. We're told that the concentration of G is 0.15. The concentration of H is 0.1. And we want to find the rate. So in this case, I'm still going to compare with the original data. I think it's the easiest thing to do. We can see that H is unchanged, 0.1 to 0.1. So this is unchanged. So H is going to have no effect whatsoever on the rate. So let's look at G, because this is going to be the only thing that's affecting the rate. Okay, so we can see that the original concentration of G was 0.2. The concentration now is 0.15. So how has this changed? We can see that it's decreased by what factor? Well, let's work it out. 0.15 divided by 0.2, and that's 0.75. So it's decreased by a quarter, which means we need to multiply the rate by that factor. The original rate was 0.4, so we'll take 0.4 and we'll multiply it by 0.75, and that gives us 0.3. More on this one and others to follow.